All right, so welcome all of you. This is the live session of our course Statistical Mechanics, and I'll be discussing one problem that we have not discussed in the course so far. It is basically an extension of ideas uh, in classical statistical mechanics. So I'll generalize the discrete spin systems to the case of n spins. So when I do this problem before you, you can join me in this session and ask problems in between and as and when you like. So if there is something that bothers you or it's not clear to you, feel free to interrupt me and I can spend time on it to explain. Right. So the problem that I will discuss now in this live session is basically a generalization of spin half system. So I will use this problem of so we have already seen spin half system of n particles in some constant magnetic field. And let us say the magnetic field is pointing along a z-axis. We can take the magnitude as b itself. So for these systems, the spin of each particle can take values such as +1 or -1, which is basically 2 into 1/2 plus 1, which is 2 values. Okay, so these are the states in which a particle can exist. And we have done this problem in the context of two-level systems. So plus and -1 are basically two levels this particle can assume in presence of a magnetic field. And we have discussed this problem, so we are not going to spend time on this problem. Today, what I'll do is basically generalize this to spin S systems. So this basically means that my particles can take values of the magnetic spin quantum number basically from 0 to plus or minus s. Okay, so basically these are 2s plus 1 values. Okay, so there are n particles, and each particle can assume a spin which is between plus s and minus s. So a typical microstate here would look like I will define a microstate in the system, and let us say nu. This is the microstate label, and this nu would be a set of values sigma 1, sigma 2, all the way to sigma n, where there are n particles. Okay, and as I've already written in the top, that the sigma i's that I have referred here in the microstate can take these values 0 to plus or minus s. What this means is, suppose for the sake of discussion, I take for example, if I take s as 3, then my n particles can stay in a microstate nu1, which is basically I can take the values for sigma 1 to be, let us say, 3, the value for sigma 2 to be 0, -1, 2, and let's say the last value is 1. So these are basically n spins. Each one of them can take values between ±3. Now, you can also visualize another microstate where these n spins have taken different values. Something like this. This way you can construct basically large number of microstates. Okay, and that would basically give you the collection of microstates, all of them sitting in the macro state, which is n comma b comma t. So this is basically a Gibbs ensemble. So these are the three variables of the macro state in the Gibbs ensemble, wherein I have a large number of microstates that I've written above. I've written only 2 of them, but we know that the number of microstates are basically 2s plus 1 to the power of n. These many microstates can exist. Okay, so if we were to take s as 1/2, then you would have 2 to the power n microstates. If you take s as 3, which we have taken in this particular case, then you had basically 7 to the power n microstates. So these are a large number of microstates for our n particles that exists in this Gibbs ensemble of n comma b comma t. Okay, so these are the macrostate variables. And if I want to develop thermodynamics of the system, so if the idea is to develop thermodynamics, which means you want to calculate thermodynamically relevant quantities such as the Gibbs free energy, such as the magnetization or the susceptibility at zero field, then you need to invoke statistical mechanics and develop this connection. So if the idea is to develop the thermodynamics, then you should basically envision the energy scale. So the correct energy scale is basically the enthalpy. And I will write down the enthalpy of a microstate, because that would be required to construct the probability of a microstate. So let me say nu is the microstate, and I want the enthalpy of this microstate. So I'll write down h nu as basically minus b times the magnetization of the microstate. Now this is the enthalpy provided there is no internal Hamiltonian, which means if spins are non-interacting. So let us start with a simple case of a non-interacting spin system. If you take Ising spins, then you have to include the nearest neighbor interaction also. But for the purpose of our sim discussion, we can ignore the details of interaction and just assume that the spins are only talking to the external magnetic field. Okay, and now I can write down the probability of finding system in some microstate nu. So if I write down the probability of finding my system in a microstate, then this is nothing but the Boltzmann factor, which is now where the energy scale is the enthalpy, h nu, over my partition function, which is the Gibbs partition function. Let's label this equation as 1. And naturally, if I look at my probability of the microstate, I can immediately write down the Gibbs partition function as sum over all the microstates. Okay, so this is the norm of the probability in the system. In some sense, it makes the probability well behaved. So let's go ahead and compute it. So this is nothing but summation over all the states, p nu. And now we have to visualize what is meant by the summation over all the microstates. So this is nothing but summation over all possible values of your sigma I. Okay. And the probability is written as e raised to minus beta. I will say that this is nothing but okay. So it has to be corrected because now my p of mu is normalized. So I will simply write down e to the power minus beta h nu. Okay. And this becomes simply plus of b times n, the magnetization m for this particular microstate. And the reason for writing this is because our h nu is nothing but minus b times m nu. Okay, so we are simply replacing our nu with we are simply reminding us that microstate is nothing but the specific set of the Ising spins that we are taking. Okay, so that's just a reminder to ourselves. And noting that the magnetization, which is an extensive variable, is nothing but the summation over all the spins. So the m here is the magnetization. It is nothing but summation over all the spins. We have n spins, and you sum up all the sigma i's, and that gives you the magnetization in terms of Bohr magneton. So we will take mu naught as the simple unit of m, and we simply sum over all the Ising spins. Okay, so that would make my partition function as nothing but summation over all microstates e to the power mu naught beta b into summation I going from 1 to n sigma I. And now, just to make things simpler, we will introduce a variable here. This G is basically a scaled variable that incorporates the effect of temperature. So if you see that there is a dimensionless variable, which simply says this is ratio of mu naught b over kBt. And now you can simply write down the partition function as summation over all the microstates, and the exponent can now be written as a product of these n exponents. And realizing that the spin of a particle, the state of a spin, is independent of the state of the spin of other particles, these product and summation can be interchanged. So it will simply come out of the summation, and it amounts to simply In fact, I can write it maybe one more step, and then I can replace it. Can write it as sigma I going from 1 to from 0 to okay. And this is nothing but you can simply compute this sum for one sigma of this exponential and raise it to the power capital N. This looks like a bit formidable, but it can be easily computed. So I can write down this sum as I can just what I can do is simply uh, take e to the power of gs outside the sum, and all the terms of the series can be written as sigma going from 0 to 2s e raised to minus sigma s. Now, if I expand this sum and multiply to e raised to gs, it's the previous sum. You can do this calculation yourself. And finally, you realize that this summation that I've written is a finite geometric series, for which the sum is readily written as 1 minus, I'm going to use two different brackets here. Let us denote the outer bracket with so I think I should write down here just sigma g. Is there a question? Okay, so there is one live question here from Sabyasachi Parida. So I'm going to take a pause here and answer his question. So he says that how do I know in which problem I have to use the partition function of the canonical ensemble and the grand canonical ensemble? So this is a simple question to sort of. The question is important, but it can be answered very simply. So in the problems where you have constant number of particles, you certainly cannot use the grand canonical ensemble, because for the grand canonical ensemble, your macrostate variables are mu, v, and t, which is basically the chemical potential, volume, and the temperature of the system. And to maintain a chemical potential to a constant value requires exchanging particles. So n cannot be a constant in grand canonical ensemble. N is a number that fluctuates. In canonical ensemble, you keep n as a constant variable. So if your system has constant n, constant v, and constant t, which is nvt, you will use a canonical partition function. We have done the problem of an ideal gas at constant nvt conditions. So you should, I'll write down basically the yeah. So since a question has come, I will go to a next page and sort of take a digression from this. So if you recall this small schematic that I keep drawing over and over. So if this is my system, and this is in contact with a heat reservoir, okay, and the reservoir controls the temperature of the system by allowing some energy exchange. So temperature can be controlled by allowing some energy exchange. So this delta E is the energy exchange between system and reservoir. To control the volume to some value v, you need just fixed walls. The walls should not be moving. And to control the number of particles, you just need the walls to be non-porous. So just by allowing the exchange of energy, you are actually looking at a canonical ensemble. And these joint system of system and reservoir, system plus reservoir, is now in microcanonical ensemble, because now the total number of particles in the reservoir and system are fixed. The total volume of reservoir and system is fixed. And the total energy of reservoir and system is fixed. So overall, if you see, the system plus reservoir is in the microcanonical ensemble. If you just look at the system alone, which is in contact with the reservoir, it is in canonical ensemble. So for that, you have to use the canonical partition function. And in our present problem that we are doing, we are in a Gibbs canonical ensemble. The number of spins is constant. N is not fluctuating here. Okay. And we are keeping a constant magnetic field and temperature. So this is the Gibbs canonical ensemble. Similar to the ideal gas under constant NPT conditions. Instead of pressure, I have magnetic field which is constant. So to control pressure in an ideal gas, I allow for volume fluctuations. In the same way, here I'm keeping the magnetic field constant. That will allow the magnetization to fluctuate. So I will be talking about mean magnetization in the system, just like I used to talk about mean volume in NPT systems. Okay, so let me just complete this partition function, and then I can get back to other questions. So here, what you see in the summation is basically the. So you can write down this as a finite geometric series sum. And finally, you can write it as you can take the e to the gs inside and make it as and by just simple manipulations, you can rewrite it as you just multiply and divide by e raised to g by 2. And then it is not very difficult to see that this is the sine hyperbolic g s plus 1 by 2 divided by sine hyperbolic g by 2 raised to power n. So this is my partition function. Developing thermodynamics is now a cakewalk. You can simply connect the Gibbs free energy to this partition function by taking a logarithm of the partition function and computing all the properties of interest. If you want to compute the magnetization, you can simply take the derivative of this Gibbs free energy with respect to magnetic field, and so on and so forth. Okay, so this completes this problem. You can do this complete problem in the limit of you can find closed forms of all these expressions, and also take, for instance, if you're interested in the small magnetic field limit, you can redo all the calculation and get these values. I leave that as an exercise, and I'll get back to your questions that you've been asking. So one question is about by Salila Das. It's about how to compute joint probability. Now, this question is not very clear in what context are you asking the joint probability. Let me just try to give you a simple example, and you can, for instance, I'm trying to now give you a simple example of two random variables. Let us say we have two random variables, x and y. And these two random variables are distributed as p of x, and the second random variable is distributed as, let us say, q of y. So these are their distributions. X is distributed as q as p of x, and y is distributed as q of y. Now, if x and y are independent random variables, okay, and this is a important conditions, then the joint probability distribution of let us say getting both x and y together, and I'm going to call it as some capital P. It will be related as the product of the individual probability distributions if x and y are independent. If x and y are dependent, then from this probability distribution you have to subtract the overlapping probabilities. So this answers the question of computing a joint probability distribution. So I'm reading other questions as they are coming up. Okay, so there is one question by Abhishek Joshi who says that can we explain Gibbs paradox in thermodynamic sense? Okay, so that's a good question. In fact, Gibbs paradox is an anomaly that comes up only in classical statistical mechanics. In quantum stat mech, you don't get Gibbs paradox. And to understand that, let me make one simple. So let me tell you why Gibbs paradox arises in classical stat mech. So I need that screen. So yeah. So yeah. So the Gibbs paradox is a problem that is present only in classical stat mech. And the fundamental reason for Gibbs paradox is basically overcounting of microstates. Okay, so the reason for this, overcounting of microstates. Overcounting of microstates happens when you're dealing with a system of n indistinguishable or identical particles. Okay, for let us say n identical particles. So if you have, let us say, there are three particles in the system, 1, 2, and 3. They're identical. So basically means that there are 6 permutations, which is basically 3 factorial, wherein if I simply change the relative locations of these particles, the Hamiltonian of the system does not change. Okay, so the weight of the microstate for all 6 of them should be taken as just one when you take it as n factorial. So unless you divide the number of microstates by n factorial, you'd be overcounting the number of microstates by precisely that factor, which is n factorial. And when you take that extremely overcounted microstates, number of microstates, let us say this is an overcounted, and this is the correct. Okay, they're related as 1 upon n factorial of overcounted to the omega of correct. So when you take the logarithm of this, okay, so let me take a simple logarithm of this, then you can see that there are enormous errors that one generates. So if you merely take log of overcounted and compute this entropy, which is basically an overestimated entropy, you will see that this is basically non-extensive. In fact, this will be super extensive. Okay, let me just write that this is just non-extensive, wherein if I scale the extensive arguments of the entropy, okay, let us say if I scale n to n lambda, v to v lambda, and e to e lambda, the overall entropy should become lambda times the old entropy. This is the meaning of extensive entropy. So if I take this overestimated entropy, I will see that my entropy does not scale extensively. So that is called as basically a reason for Gibbs paradox. And now what happens is, as if I go with this overestimated entropy and try to compute mixing entropy of 2 identical gases, I will compute, or I will observe that if 2 identical gases at same density and temperature are mixed, then it basically gives rise to a non-zero entropy of mixing. So if I take, for example, 2 gases that are identical to each other, okay, and I am taking both the gases at, let us say I'm taking N1, V1, and T1, and I'm taking N2, V2, and T. So both the gases are taken at the same temperature. Okay. And I further assume that the number density on both the sides are the same. And I allow them to mix by removing this wall. Then what should I observe? Should there be an entropy of mixing? There should not be any entropy of mixing, because this is a process where you have not seen anything irreversible happening. In fact, the final state of the system, which is here on the right hand side, is the same as the initial state of the system. They cannot be distinguished. But if you use the overestimated entropy and compute the entropy of mixing of 2 gases at identical temperature and number density, then you will see an entropy of mixing which is non-zero. And that is called as Gibbs paradox. To correct this Gibbs paradox, you have to start from the correct estimation of number of microstates, which is basically this omega corrected, take its logarithm, and then compute the correct entropy. And if you redo this calculation of mixing, you will see that entropy of mixing comes out to be 0. So this is how Gibbs corrected this problem. And historical reasons, we call this as Gibbs paradox to honor his efforts. So So the question by Akash is why is the energy scale in the Gibbs canonical ensemble given by E plus PV and not E plus P delta VV? Okay. So the energy scale in Gibbs ensemble is not incremental energy scale, it's the total system's energy. So this is the total internal energy plus PV. I mean, it is not DE plus PdV, which would be basically by our logic, it would be the total, by first law of thermodynamics, this would be nothing but the incremental energy supplied to a system, which is reflected into by some amount of work done, which is PdV, and some energy rise, internal energy rise, which is dE. We are talking about the total energy scale in the problem. So, which is basically the internal energy, that is E, and to this we add the pressure volume work, total volume, and that is nothing but our enthalpy of the system. So E plus PdV is not the enthalpy of the system, it's E plus PV, which acts as the enthalpy and the new energy scale of the problem. Okay, so our entire system is sitting at volume V, so we should compute the energy required to develop the entire system which is now sitting at volume V at pressure P. So in some sense, you can see that we take PdV and integrate over the entire volume. So you get PV as the total pressure volume work, and your system is now sitting at the energy E, which is basically this guy. E is simply a summation over all the kinetic degrees of freedom, P square by 2m, and that is basically the pressure volume work done by the reservoir. Total pressure volume work done by reservoir to bring your system at this final volume. So together, E plus PV gives you the enthalpy of a system, instantaneous enthalpy of the system. Okay, and that sets the energy scale of the Boltzmann factor. So in Gibbs partition function, you will always use the enthalpy as your energy scale. So this would be your enthalpy. Okay, so you have to sum over basically all the possible. So you will say this is the microstate enthalpy, and naturally you have to sum over all the microstates. So this is your Gibbs partition function. Okay, so Sambhav Antriksh asks me, what is the Ising model? So we have not discussed Ising model in this chapter, but Ising model, well, we have discussed one non-interacting Ising model. Ising model is the simplest, I would say, paradigmatic model of phase transitions, or the simplest model of phase transitions in magnetic system. Now, for phase transitions, you need some interaction, some collective behavior that sort of dominates a single particle behavior at low temperatures required. So the Hamiltonian of the Ising model is written as some minus J. I'll explain what is J. Sigma, I'm going to write down a one-dimensional Ising model. I running from 1 to n being the number of particles in the number of spins in the system, and these are the spins Si plus 1. Now the reason I've written I and I plus 1, it already tells you that I'm talking about a nearest neighbor Ising model. So I have conveniently ignored I plus 2 interactions and so on. So this is the nearest neighbor Ising model. And naturally, if I put I equals to n in this summation, then I get the second S as n plus 1, which does not exist in the system. So I have to assume what is called as a periodic boundary condition, that the n plus 1th spin is basically in Sn, S1. So this is called as the periodic boundary condition. And if you read the literature, this simple 2-spin or nearest neighbor spins at very low temperatures can lead to symmetry breaking or phase transitions. So in the Ising model is known to break symmetry in 2 dimensions, and this was analytically solved in 2 dimensions by Lars and Sagar. It said that there are finite temperatures phase transition in this system at non-zero temperatures. And just to sort of finish this argument, the J here is called as the exchange interaction, okay, or exchange coupling. So if you keep J as greater than 0, then the low temperature ground state is actually of paramagnetic ordering. So you have got all the spins. So there are 2 types of paramagnetic ordering. Both have equal likelihood. All up or all down, both lead to your reduction in the total energy. And if you take J less than 0, then it leads to, sorry, I should say this is ferromagnetic ordering. I'm sorry. This is called as ferromagnetic ordering. And this is called as antiferromagnetic ordering. Okay, so antiferromagnetic is also a highly ordered state, but here the adjacent spins are sort of aligned in opposite manner. Again, you have 2 different ways of setting this antiferromagnetic ordering. So these are the 2 these are the 2 ground states for the different values of J that we can speak of. Okay, and this also tells you how the finite temperature phase transitions basically mean symmetry breaking. So if you see at low enough temperatures, the system can go to plus m or minus n in the case of ferromagnetic ordering. But at high temperatures above Tc, the system's magnetization is 0. So the spontaneous transition into plus m and minus m is basically a result of this symmetry in the Hamiltonian, which is broken spontaneously. And that symmetry is the up-down symmetry of the Hamiltonian. If you read the literature, you understand what is meant by this up-down symmetry. Up-down in the sense that the Ising model is discrete and it has, so this is a discrete symmetry that is broken, and that leads to a ferromagnetic ordering. So the question by Salila Das is, what is meant by interacting particles in statistical mechanics? So interacting particles are simple. So far we have written the Hamiltonian of an ideal gas, which is a non-interacting system, as simply summation over all the kinetic energies. Okay, the interaction potential is basically taken to be 0. So the interaction basically is over, let us say, I should, if I write down the interaction, I should be careful in saying that this is, let us say, I naught equal to j, and I will take a half outside because I don't want to double count I and j, and this is the Rij. Okay. So this is usually taken to be 0 for non-interacting systems. And the reason why I take it to be 0 is because the problems are, it simplifies the problem. Otherwise, if you take interactions, then computation of partition function can get a bit tricky, and and so this is often ignored. In the first course to StatMech, we don't really include the interactions, but one can include these interactions and also do statistical physics of interacting systems. And yeah, so the tools of the tools or techniques will not change. Calculations will become slightly more tedious. So how is entropy? So next question is by Sabyasachi Parida, who says that who asks that how is entropy related to number of microstates, and why entropy, not other thermodynamic parameters? Okay, so entropy, if you look at, is basically a measure of disorder. So do we agree with this or not? Entropy is a measure of disorder. Now, the question why is entropy related to number of microstates is very easy to answer now. Suppose I have only one microstate accessible to my system. Then there is no disorder, because every time I see the system, it is seen to be sitting, politely in that state. It is like if there is only one seat in the classroom, and a student comes, he can sit only in that seat. But if I increase the number of seat, or let us say vacancies in the class, then the student can take any seat in the classroom. So it simply means that the number of vacancies or the number of states is a direct measure of disorder, because now the particle or the student can come and sit on any vacancy. And for instance, yeah, I need the yeah, thank you. So simply speaking, higher the number of states accessible, higher will be the disorder. Higher the number of states, and leads to higher will be the disorder. Okay, so I can give a simple example in terms of our two-level system. Suppose you say that if you look at n spins and all of them are up, okay, which means you are looking at n spins, all of them aligned in one direction. Now this would be the case, let us say, at t equal to 0, perfectly ordered. Okay, now clearly the number of microstates accessible to this system is just one. There's only one way the system can sit. So the entropy is basically ln, if I forget Boltzmann constant for the time being, let us say Boltzmann constant is 1, then this is 0, the perfectly ordered state. That is what we expect. But let us say I increase the temperature slightly above 0, such that one spin is now excited, or it is sort of disordered. Rest of the n minus 1 spin continue to be in the same direction. So this is one guy which is now down. So clearly the number of microstates here is basically n. So there are n ways in which one guy can sit in the minus 1 state, and n minus 1 guys can sit in the up state. So the entropy is now dramatically increased to ln n. So this is called as higher disorder. Isn't it? You agree that the first case you had only one state, one microstate, and the second state you have n microstates. Clearly you are more disordered in the second state. So that is why we say that entropy is a measure of disorder, and hence it's a measure of number of microstates in it. Now the question is, if entropy, that is one thing to say. Second is, why is entropy only a logarithm of omega, not n or n square? Okay. So first, entropy is a measure of disorder, and entropy increases with the number of microstates. This is one statement. But why is entropy logarithmically related to number of states? And this is because you want the entropy to be additive or extensive. So if you take two systems with number of states being omega 1 and omega 2, okay, which means if you take the joint system, will now have access to omega joint, which is nothing but the product of these two individual number of states. So if you compute the entropy of the joint system, this will be, again, I will drop the Boltzmann constant for the sake of simplicity and write it as omega joint. You expect that the entropy should be the sum of the individual systems, right? And it does come out to be the sum of individual systems. So this is taken as ln of omega 1 into omega 2, which is nothing but ln of omega 1 plus ln of omega 2, which is nothing but the entropy of the system 1 plus entropy of system 2. So the reason why we take entropy as the ln of omega is because of the reason that we want entropy to be additive. Okay, so this is the reason why we take entropy as logarithm of microstates. So if you take two systems with individual states omega 1 and omega 2, naturally the joint number of states is omega 1 times omega 2. And if you compute the entropy of the joint system, you will find that this has to be the sum of the individual entropies. Right. So are there any more questions? Okay, so there is one question by Deep Muzumdar who says that, so I can answer this question without writing anything. So he's asking about the pattern and types of question for the offline exam. So there will be about 6 questions for a 3-hour exam. Some questions will have small parts, and you will be asked to do some simple calculations. That has been the theme of our course. And practically all the problems that I've done in the class in front of the camera and the last worked out examples, problem solving demos, you should look at that and do some problems on paper. The content of the final exam is majorly from the problems covered in the class. And any new problem that you may encounter would not require different concepts that we have not discussed. So the scope of the end semester exam is basically testing your ability to use the concepts that have been covered in our course to some problems. So for instance, if you know how to use the simple probability distributions, the 3 important distributions that we have studied in our course in chapter 1, let us say the Poisson distribution or the Gaussian distribution, then you should be able to do some problems, because these are the major distributions. I will ask problems from these distributions. In chapter 2, we have covered some very important postulates: the canonical ensemble, the grand canonical ensemble, the Gibbs canonical ensemble. So I will ask you to do some simple problems to set up the energy scales, to compute properties in thermodynamics, for some simple case studies such as an ideal gas or a spin system, and practically everything that we have done in the class in front of the on the camera. Uh, and So this would be a good time to look at your assignment sets. The solutions have already been mailed to you, and if there are any queries regarding the solutions that have mailed to you, please get back to us. My TA is always willing to help, and we will be able to solve your queries um, in the shortest time scales possible. Well, there will not be direct derivations in the final exam, because that is not going to test your concepts at all. We'll give you numerical problems. Um, if something has been derived in the class, then asking the same question again doesn't make sense, right? So we need to see how well you can apply the concepts and do problems. So my recommendation would be to go back to the tutorials, not tutorials, go back to your problem sets, look at the solutions, see how the problems were done. Try to think of developing your own problem. So, for instance, in Grand Canonical Ensemble, if I have asked to compute mean number of particles, in Grand Canonical Ensemble, particle number fluctuates. Okay, so if you're looking at ideal gas under a Grand Canonical setting, the particle number will fluctuate. Try to compute the mean number of particles. If you have done that, try to compute the fluctuation number of particles. So try to construct your own problems in your mind, and that should help you basically score well in the exam. And similarly, if you want to look at spin system in Gibbs ensemble, try to construct mean magnetization fluctuation. These are very simple things that you can compute using techniques that have been developed systematically over the past 3 months. Okay. So if you before the exam, if there are any questions, I think you can mail it to us, or there is a chat room available where queries that are posted will be answered on the same day. And so there should not be an absolute necessity of a live chat session again, because I don't think uh, that would be necessary. But if you can, if there is a calculation that is not complete and you would like to show it to us, just take a scan of it and upload it. I think uploading snapshots of your calculation is possible in the chat room, and we can immediately answer it. So there should not be any issues. Now there is so Muzandar is asking a question about what textbook would I recommend to understand the subject. Well, there are many textbooks in this area, and so I would not be recommending one over the other, because every author has his own beautiful style of representing the subject, and he uses his or her uh, topics of interest. So choose a textbook which helps you to understand better. What has worked well for me need not work well for you, right? So I will only say that the textbook for this course was Mehran Kardar for chapter 1 and chapter 2. And for the final chapter, which is quantum statistical mechanics, I have used the textbook of David Chandler. not because they are the best books, but because they are the most one of the most popular textbooks that are used across universities in India and abroad, and they are helpful. That is not to say that other textbooks are not to be used. It is purely a matter of personal perspective, and you are free to choose whatever you want. All right, so that is the end of this live session. So there's one question that I will take by Munendra Dasanagiri, who says that how to choose the correct model or ensemble to solve the system. Okay. So as I have already said um, before, that if your if your system is sitting at constant number of particles, volume, and energy, then you have to choose the microcanonical ensemble. That's the simplest ensemble where everything is constant. N, V, E. All extensive variables are constant. This is the microcanonical ensemble. Now you allow for energy fluctuations. This will give you a possibility to control temperature. So this is like a system in contact with the heat reservoir, where N and V are constant because reservoir is not exchanging particles with the system, and the volume is also constant. So there are fixed walls that do not allow the volume to change, but the energy of the system is exchanged with the reservoir. So this problem, you will be looking at the canonical ensemble. So to develop connections with thermodynamic, you would compute the canonical partition function and connect with the Helmholtz free energy by taking a logarithm, and then from there use the first law of thermodynamics and develop quantities of interest. If you allow volume also to fluctuate, then you are actually using a reservoir that has twofold task: control temperature and control pressure. Temperature is controlled by allowing energy exchange, and pressure is controlled by allowing volume exchange. So now you have two fluctuating variables: internal energy to control temperature and volume to control pressure. So volume and energy are fluctuating variables. And under such a setting, you will use the enthalpy of the system as the energy scale. This is called as the Gibbs canonical ensemble. So instead of E, your energy scale will be E plus PV. Okay. And here, your enthalpy fluctuations will be related to heat capacity at constant pressure. Just like in canonical ensemble, your energy fluctuations were related to heat capacity at constant volume. And finally, if you allow the number of particles also to fluctuate, then your chemical potential is constant. So you are now looking at a grand canonical ensemble where the macro state is specified by chemical potential, volume, and temperature. And the fluctuating quantities are number of particles and internal energy. So N and E will fluctuate. Now, when N and E fluctuate, the energy scale is basically again enthalpy, but this is a chemical enthalpy. So your energy scale will be now E minus mu N. Okay, so that's how you see which quantities are constant and what quantities are fluctuating, and then set up the ensemble and then set up the partition function. So the systematic way of doing is if you have a system in front of you and you have a reservoir, find out the fluctuating quantities, find out the constant quantities. The constant quantities will be basically your macro state, and the fluctuating quantities will set up your energy scale, whether it is internal energy or enthalpy or whatever it is. Then you write down the probability to find a system in a particular microstate. Of course, after you have visualized the microstate in the system. And actually, once you have the probability of finding the system in a microstate, you can then write down the partition function, which is simply the norm of this probability. Once you have the partition function, you can set up connections with the thermodynamics by taking a logarithm of this partition. And after you have the energy scale, use the first law of thermodynamics or any thermodynamic law and compute quantities of your interest. So please go through our course completely, and especially the part where we have discussed the fundamental postulates of classical stat-mech. And this has been systematically discussed in the class also, and we have done problems. So please do the problems. My recommendation would be not to choose a particular book, but to always do the problems and take your assignments, problem sets very seriously, and mail your calculations to us if you think they are an improvement over our calculation, or if you are unable to do a calculation, you are stuck somewhere, something is not clear, you can just take a snapshot and send it to the chat room, and my TA will take care of it. He's more than equipped more than adequately equipped to handle your queries. All right, so now we'll end this session. If there are further questions, we will take it in the chat room or through your NPTEL platform. Okay. All right, so thank you very much. All the best for your exams.